Hi, my name is Scott Simpson, and in this tutorial we'll be covering intermolecular forces of pretty much all forms of matter in chemistry. So we'll be looking at solids, we'll be looking at liquids, and we'll be looking at gas phase molecules. So if we first start, there are three types of bonding we can have essentially. We can have metallic, which we are not going to get into. Actually, let me erase all of this. We're going to build a diagram, and we're going to talk about each of the forces, and we're going to determine what type of forces are in each one of our systems. So for this, you'll have to cover dipoles, and that's essentially it. So, and Lewis structures, I suppose. All right, so we have metallic bonding. Metallic bonds, we have ionic bonds, and then we have covalent. All right. So let's talk about each one of these types of bonding. So metallic bonds, this is usually in solids between metals. So you have a metal surface, and they call it a sea of electrons. You really don't need to cover it for general chemistry purposes, but if you're interested, there are a bunch of textbooks that you can check out. It's a very interesting world. I work a lot of it in my research, so that's kind of tricky. We won't talk too much about it, but all you really need to know is what happens in metallic bonds is if we have our nuclei here, we kind of imagine that the electrons can move freely throughout the system, and that's why they call it a sea of electrons. The electrons are kind of just flowing everywhere inside of the solid. So that's what's occurring in metallic bonding, and it makes it very strong, very malleable. What I mean by malleable, it's easily bent. Next, let's talk about ionic bonds. So ionic bonds are usually between a metal and a non-metal. So an example of this would be something along the lines of sodium chloride. And what happens in ionic bonds is there is a positively charged cation, so cation is positively charged, and then there's a negative anion, so that's the molecule, the atom that becomes negatively charged. So in this case, sodium has a positive charge on it, and chlorine has a negative charge on it. And there's an attraction between the two, and there's no true bond, I guess, that forms here. It's an electrostatic interaction, so a positive and a negative like to be close to one another. That's essentially it. These bonds are very strong. They're considered the strongest out of all of these. Now, covalent bonds. Covalent bonds are whenever you have the bonding between a non-metal and a non-metal. So an example of this, a covalent bond, would be something along the lines of Cl2. So you have two chlorines, and they're sharing the electrons between them. I've kind of neglected the other valence electrons, so let's just draw those in, just to be consistent. So they're sharing the electrons in a covalent bond. We can talk more about what's happening in covalent bonds at a later date. If you check out, I should have some organic videos up. We'll talk more about orbital overlap in a different YouTube video. But there are different types of interactions that can happen between molecules or in solution. So let's first consider covalent bonds. So we can have polar and non-polar covalent bonds. So we can have polar bonds interactions, and then we can have nonpolar. So, we can determine from this there's another subset of interactions, but what type of molecules are polar and what type are nonpolar? Well, we covered this in a previous YouTube video, but just for quick clarity, something along the lines of H2O is polar, whereas something like methane is nonpolar. This has an overall dipole moment, whereas methane does not have an overall dipole moment. So things that have an overall dipole moment are considered polar. Things that do not have an overall dipole moment are considered nonpolar. All right, so what interactions are important for polar molecules? So there are a few that we can have. We can have dipole-dipole interactions. We can have hydrogen bonded, or bonding. And there are also London dispersion forces, or van der Waals forces. Now, nonpolar molecules can also have dispersion forces too. In fact, that's really the only intramolecular force that they encounter. Now, let's give an example of each of these. So dipole-dipole interactions. If we have something along the lines of HCl, we can have a dipole pointing this way. Now, since this end has a partial positive and this end has a partial negative, if we end up having another HCl molecule next to it, it's going to align itself in such a fashion to have its partial positive, where the hydrogen is, be near the other molecule's partial negative, where the chlorine is. So let me just draw this out. So if you see, the dipoles are pointing in the same way. And what happens is there's a sort of energy gain associated with this. So since there's a partial positive here, partial negative here, partial positive here, partial negative here, there's an electrostatic interaction which attracts these molecules and saves some energy. So there's an attraction between these two guys. So what about hydrogen bonds? So hydrogen bonds typically only happen when we have hydrogen with a certain atom. So H bonds. They only happen with HF, HN, and HO. So what is a hydrogen bond? So let's draw out a carboxylic acid. So that's basically where we have something along the lines of this. Or no, let's go with water. Water is a simpler example. It's almost like a dipole-dipole interaction. It's just classified a little differently. Excuse me. So again, we have the partial positives here, partial negatives up here. And if we have another oxygen, say one over here, kind of same thing, partial negative, partial positive, partial positive. These oxygen and this hydrogen are going to be attracted to one another due to electrostatic reasons. So there's going to be an attraction there. And now this is considered a variable strong force. So this can have a strength anywhere from less than 1 kilojoule per mole to up to 40 kilojoules per mole. Whereas dipole-dipole interaction usually is around 25 kilojoules per mole. All right, what about dispersion forces? Well, dispersion forces are easy to think about. When you think about two large interacting bonds. When we think about two interacting homogeneous gases, so that are localized in a sphere, let's say. So a sphere of non-interacting homogeneous spheres that have the same electron density. And what ends up happening is so there's electrons smeared out over both of these. And they approach one another. As they approach one another, let's say just by this direction, what's going to happen is this is going to end up coming a bit closer, and it's going to malform this guy into kind of an egg shape. Where we form a set of instantaneous dipoles. So let's call this molecule A and molecule B. On this side of molecule A, you're going to have a partial negative, but on this side, you'll have a partial positive. The same thing happens with B. You'll form a partial negative over here and a partial positive. And there's a set of weak dipole moments that form. But they're not considered a very strong dipole moment. It's a very, very weak dipole moment that only happens instantaneously. And it's the weakest of all the forces. So it's very, very weak. It's usually on the order of 2 kcals per mole. Or I mean 2 kilojoules per mole. So, we have left out one more interaction. And this is the interaction of a dipole with an ion. So it's actually a cross between ionic bonds and covalent bonds. So what ends up happening here is it's something along the lines of sodium, which is positively charged, and we have something that is covalent in nature. We have, let's say, water. So we know that water, the oxygen end is partially negative, and the hydrogen ends are partially positive. And we know it has an overall dipole moment pointing in this direction. Now our sodium is positively charged, and we have a partial negative on our oxygen. So there's going to be an interaction between this sodium and this oxygen, which is going to lower our energy. And what happens is it will actually dissociate the ionic solid. So you've seen this before. When you take salt, just common table salt, and you throw it in water, it dissolves, right? I previously said that ionic bonds are the strongest, but what's happening is these bonds are being broken by these ion dipole interactions. So let's include this ion dipole on our chart. So, you've heard the term like dissolves like. Well, what does that mean? Well, if we have similar interactions, we're going to dissolve similar things. So something like CH4 methane, C2H6 ethane. They're going to be dissolved. They can be dissolved in the same solution because they only have dispersion forces and they're both nonpolar systems. But what about if we have something like methane and water? These two are not alike because water is polar. It has hydrogen type bonds, dipole-dipole type interactions can also occur, and it also has dispersion forces. But we only have nonpolar on this side for methane. So since they are not in the same category, they do not like to be immiscible of one another. So they will not mix together. You can get slight mixing, but it's going to be very, very small. Whereas if we have something like Water. So we have H2O. And let's say we have ethane, or ethene. We have, let's go with HCl. And then let's go with ClCH3. So, which is the most likely to be dissolved in water? Is a good question. Well, if you've been in lab, you may know the answer to this question already, but let's figure it out. So we have to draw dipole moments for these guys. So first, we have to draw our Lewis structures in order to determine if this system has a dipole moment. So, CH2, CH. So let's draw our dipole moment. Does this molecule have a dipole moment? The answer is no. There is no overall dipole moment. There is dipole moments of the bonds, but there is no overall dipole moment, which is an important point. What about HCl? HCl, yep, there should be a dipole moment. And it should be pointing in the Cl's direction. Now, what about ClCH3? It's going to look something along the lines of this. H. I'm not I guess I'll draw in. I should. Specifying if it's coming out or in the board, that sort of thing. Because this actually has a tetrahedral geometry. So, there is a dipole moment pointing this way. Now, which of these will be dissolved in water? Well, these two have dipole moments, right? So that means that they're polar. Whereas this guy has no dipole moment. We've just shown that. So that means that these two will be able to be dissolved in water, but this one will not be. And that's what's meant by the term like dissolves like. So what you'll have to do is go through the diagram I've drawn, determine if each molecule is polar or nonpolar, and what type of interactions it can have. And then you'll be able to determine if that compound will be soluble in whatever solvent you're trying to look at. Alright, so that's all I have for this section. If you have any questions or comments, please leave them below. And thank you very much.